Okay, so I want us to focus on rational functions in this portion of the lesson. And I want to take a little time to review rational functions and some characteristics of their graphs. So you'll need your calculator. So when we want to graph functions, any function, we go to y equals. And I'm going to go ahead and just put in f of x, or y equals the 1 over x. So 1 divided by x. And I want us to draw that. So I'll push graph. And then let's sketch what we see on our calculator. So this particular function kind of looks like this. Because in just a few minutes, we're going to look at some things and maybe see what kind of similarities, maybe, what characteristics they have in common. All right? And so there's the graph of 1 over x. This is not a continuous function because there is a gap at x equals 0, just so that you will know if we press, oops, that's not going to work. If I press trace, then at 0, notice I do not get a y value. And that's because that x is not in the domain for this function. There is no y value for this function at x equals 0. Okay, so now let's move on to 1 over x squared. So go into y equals, I'm going to do these one at a time. So I've got 1 over, there's my x, I will square my x, and then I will press graph. And so what do we see is we see a graph that behaves like this. It's kind of sad, but anyway, you get the idea. Okay, then let's go to the next one. And here in y equals, it's x divided by. Okay, I'm just going to clear that out. So x divided by, I have to open the denominator in parentheses and then do x squared minus 1 and close the parentheses. Now I will graph. And let's see what this graph looks like. Okay. Well, that's interesting, but that's okay. Here's what we have. We have a graph that looks something like this. And then in the middle, we have a little doohickey that looks like this. A little branch that looks kind of like that. Okay. All right. And then moving on, let's look at the next one. So y equals, I'll clear, and I need to do x squared, squared, and I will divide by, open parentheses, x cubed. So I have to use my caret key, type in my 3, get out of the exponent, so use your right arrow key, and then minus 27, and then I will close that, and I will graph. And let's see what this graph will look like. Okay. So this graph, looks something like this. And then lastly, let's go in and take a look at, we have to open the numerator with parentheses and then x minus 2, close the numerator. I need to divide, and I'm going to open x raised to the third power, get out of the third power, plus 3x squared, plus 3x, plus 1. Close the denominator. And I will graph. Okay. Okay. So, All right, so this particular graph looks a little bit like all right, it looks something like that. So here's what I want us to do now that we have looked at a variety of rational functions. And these are rational functions because they are written in the form of a fraction where a variable is in the denominator. So this is a form of a rational function. And what I want us to focus on is this. I want you to look at each of these graphs. Forgot my little arrows here. I want you to look at each of these graphs, and I want you to start looking at them from the origin, and I want you to look at the graph of each of these moving away from the origin as x approaches negative infinity and as x approaches positive infinity. So in other words, I want you to look at the graph as you move away from the origin, and I want you to describe the behavior of your y values. So if we take a look as this particular graph, looking at this one, as you move away from the origin in the negative x direction, and you move away from the origin in the positive x direction, what do you notice about the y values? Well, notice that each of these appear to get very, very close to a horizontal line or a horizontal axis. In other words, they get very close to y equals 0. And this is a horizontal asymptote. Asymptotes are those lines or graphs that your graph gets very close to, but doesn't necessarily touch. Okay, if you look at this graph, again, we're looking at strictly at the graph moving away from the origin. As you move away from the origin in the negative x direction and you travel along this graph, as you look at the graph, as you move away from the origin, the graph begins to decrease, and you'll notice that as your x's go toward positive infinity, the closer the graph gets to a y value, which there appears to be a horizontal asymptote there, and yes, that would be at y equals 0. Here we have a graph. As you look at the graph, as you move away from the origin, you know, you're going to be traveling along this one. The further the left you go for your x's, your y values get very, very close to this x-axis. Same thing is true as your x's or as you move away from the origin for this branch as well. So all three so far, all three of these graphs, as you look at the graph and you move away from the origin in the positive and negative direction for x, the graph also gets very close to a horizontal asymptote. Same thing here. There's a little horizontal asymptote. There's a horizontal asymptote. So all three of these have, what they have in common is all of the graphs have a horizontal asymptote. Specifically, all of these 5 graphs have a horizontal asymptote whose equation is, let me get a little pen here. Your HA is at y equals 0. So each of these graphs have a horizontal asymptote. A horizontal asymptote is a line that each graph approaches as you move away from the origin in the positive and negative x direction. Okay, so the question is, let's see if we can make there is something about the equations of each of these functions that tells us that we will have a horizontal asymptote at y equals 0. I can look at this function, look at these three. Each of these three, as well as these two, each of these, there's something significant about the equations that indicate that each of the graphs will have a horizontal asymptote at y equals 0. And what that is look at the degree of the numerator and the denominators. And what I hope you recognize is that the degree of the numerator is smaller than the degree of the denominator in each case. And even though this is 1 over x, this x is raised to the first power. Since the numerator does not have an x, it's really technically x to the 0 over x to the first, because anything raised to the 0 power is 1. So in all of these cases, the degree of the numerator is smaller than the degree of the denominators. All right. Now let's talk about, let's see if what these graphs look like. Okay, since we've talked about the degrees of the numerators here being smaller than the degrees of the denominators, look at what these next examples have. The next examples, you'll notice that all of the degrees are the same. So out of curiosity, I wonder what the graph will look like. Well, we're going to find out. So be careful how you put this in your calculator. I'm going to go in and clear this out. I need parentheses around my numerator, x minus 1, and I will divide that by x, and now I will graph. Okay, so this particular graph looks very similar to, they look very similar to these, but what you might notice is, that, if I can draw, your graph kind of looks like this. And if you were to draw, there is a horizontal asymptote that goes between those two branches of the graphs. As you look at this graph, as you move away from the origin, this graph does approach or get very close to a horizontal asymptote. Okay, let's do this one. Oh, by the way, what is the horizontal asymptote here? Well, it appears that the graph or the equation should be y equals 1. So here's what I can do. I'm going to go into y equals, and I will type in y equals 1 in y2, and then graph. And then you can actually see that horizontal asymptote. All right, now let's go in and let's clear that out. And we will do, open the numerator to x squared minus 4, close the minus 4, divide by, open the denominator, x squared. Oh, I didn't have to, but since I did, I'm going to close the parentheses. I didn't have to put parentheses around the denominator, but I will graph. Does this particular graph have a horizontal asymptote? And it appears that it does. The graph looks, something like this. And there appears to be a horizontal asymptote there. Now remember, a horizontal asymptote is a line that the graph approaches as you move away from the origin in the positive x and negative x direction. So as you move away from the origin, is there a y value that the graph is approaching? And the answer is yes. Now, I'm wondering if you can tell maybe what the equation of that horizontal asymptote would be. And I think it appears to be 1 again. So just to put it in perspective, I'll go to Y2, type in 1, and graph. And sure enough, that looks like where the horizontal asymptote is. Okay, then my next one, I will clear out everything. Let's go about 2x squared. So 2x squared, divide by, open the denominator, x squared minus 1, close the denominator, and here's my graph. And this one, this particular graph, it has, you know, a horizontal, it has a graph that looks something like this. Not perfect by any means, but there is, notice how these portions of the graph kind of flatten out. So appears that there is a horizontal asymptote. Now, I don't think it's at 1. Let's see if it's at 2. So if I go into y equals and I go to 2, y2, and type in 2, there you go. So just don't forget that even though it looks like the graphs are touching the horizontal asymptote, if I press trace, and I type in, let's say 3. Now watch as I do this, and for my calculator, it's really difficult to see. So your y values, as I move along this graph, as x gets bigger and bigger and bigger, the y values are decreasing, and they continue to get closer and closer and closer to 2. So even though that cursor looks like it is sitting on or intersecting the horizontal asymptote, it is not. It's getting very close, and it appears that it touches or intersects, but it doesn't. All right, so for this one, the horizontal asymptote was y equals 2, and I didn't write this one on here. This one was y equals 1. All right, now for this one, I'm going to go to y equals, and I'm going to, I have a negative, so I got to be careful. So I'm going to type in my negative. Nope, I'm going to clear that. I'm going to clear everything out. So there's my negative. I will type 4x raised to the third, and then get out of that exponent. I will divide, and I will now type in parentheses 2x raised to the third, get out of the third, minus 1, and close the parentheses. And since I changed my window on that last example, I'm going to do a quick draw, which is zoom, and I'll choose 6. And here comes the graph. Oops, sorry. Oh, that must be a shadow off of the window behind me. Okay, so here we have a graph, and that's interesting. And then we have another portion here. So does there appear to have a horizontal asymptote? Yes. But what does the equation appear to be? Well, it appears that it will be a negative, and so I'm thinking it'll be -2. So go down to y2, type in -2, and graph, and sure enough, that's what the case is. That's what the horizontal asymptote is. So the equation for this horizontal asymptote is, not 1/3, is y equals -2. All right. Okay, so then next we have a function, 2x cubed minus 2, all divided by 6x cubed plus 3x squared plus 3x plus 1. And this graph, it'll be kind of a pain to type in. However, as we type this in, I'm wondering if you could determine what the equation of the vertical asymptote, if any, would be. So I'm going to go into y equals. I'm going to clear out everything that I've got in there. So I need to open parentheses for my numerator, and 2x raised to the third minus 2. Close the numerator. I will divide by and open the denominator, 6x raised to the third. Get out of the third, plus 3x squared, plus 3x, and then plus 1. It's a lot to type in. So it's a lot to type in, but when we do, we will get a graph that looks, okay. So the graph looks something like this. Now, as you look at this graph, it really does appear, it really looks like there would be a horizontal asymptote at y equals 0. But I think not. I think if you go back and you look at the equation for your horizontal asymptotes here on the first example, and the second example, and the third example, and the fourth example, I'm going to say that the equation for the horizontal asymptote for this is going to be 1/3. Because what I notice is this. If the leading coefficient of x is 1 and the leading coefficient of x is 1, and you divide, you get 1. Here, the leading coefficient of x squared and the leading coefficient of x squared are both 1, and you divide, you get 1. On the third example, notice that the leading coefficient of the numerator is 2, the leading coefficient of the denominator is 1. 2 divided by 1 is 2. And then on this one, we said the graph had a horizontal asymptote at y equals -2. And you see you have a negative out front. The leading coefficient of x cubed is 4. The leading coefficient of the denominator is 2. And when you divide, you get 2. So leading coefficient for this example is 2. Leading coefficient of the denominator is 6. If you take 2 and divide it by 6, you get 1/3. So I'm going to go into y equals, and it's going to be a bit crowded, but I'm going to do this anyway. So I type in y equals 1/3, and then I will graph, and there you see it. So how do you determine the horizontal asymptote from a rational function's equation? You have to identify the degree. Notice that the degree of the numerator and denominator are the same for each example. The degree of the numerator is 3. The degree of the denominator is 3. The degree here is 3. The degree here is 3. And so you know that this will have a horizontal asymptote, and you find it by dividing the coefficients. So in the first 5 that we did, the degree of the numerator was smaller than the degree of the numerator, and we always had a horizontal asymptote at y equals 0. When the degrees are the same, then your horizontal asymptote, your HA, will be y equals c, some number, And you determine that number by dividing the leading coefficients of the numerator and denominator. So if we've looked at the example where the leading coefficient of the numerator is smaller and the leading, no. If the degrees of the numerator and denominator, I'm going to try that one more time. When the degree of the numerator is smaller than the degree of the denominator, you know you will have a horizontal asymptote, y equals 0, always. When you have a rational function whose degree of the numerator and denominator are the same, you will have a horizontal asymptote. And to determine that horizontal asymptote, you simply divide the coefficients. 4 over 2, keeping it negative. 2 over 3 reduces to 1/3. 2 over 1 is 2. 1 over 1 and 1 over 1. So those are the scenarios where you do have a horizontal asymptote. Now, let's graph this next example at the bottom to see if it has a horizontal asymptote. I'm going to clear this out, clear out my wet equals. I'm going to type in my numerator in parentheses, x squared minus 1. I will close my parentheses. I will divide by x. Now, as we press graph, what do you notice about the equation and the degrees? And now take a look at this graph that we have. So notice that this graph, as you look at this graph, moving away from the origin in the negative x direction, the graph, the y values are not approaching a finite number. And neither does the graph or the y values as you look at this graph moving away from the origin in the positive x direction. We have our, your y values are not approaching any finite number either. So this particular function, the graph does not have a horizontal asymptote. So how did I know that ahead of time? Well, I knew that because the degree of the numerator is bigger than the degree of the denominator. Now, I will say that this particular graph does have an asymptote. It's considered an oblique asymptote. And I'll put this in so that you can see it. And here comes the equation for the oblique asymptote. Notice that the oblique asymptote is a line. This graph is a line. It's just not horizontal. It's just not a horizontal line. But again, this is a way that we can determine the end behavior of a function as you look at the graph moving away from the origin in the negative x direction. Notice that the left end behavior of the original function behaves the same way as the oblique asymptote. Let me draw this. And let's see, we have something that looks like this and something that looks like this. My graphs look bad, but anyway, you get the point. As your graph moves away from the origin in the positive x direction, notice that the right end behavior of this graph behaves the same way as the oblique asymptote. So when the degree of the numerator is larger than the degree of the denominator, you will not have a horizontal asymptote, but you will have an oblique asymptote. And so the end behavior of your rational function will behave the same way as the oblique asymptote. All right. Now let's move on to the next one. Our next example is another rational function. You'll notice that the degree is 3 in the numerator, the degree is 2 in the denominator. So this graph will not have a horizontal asymptote, but what it will have is an oblique asymptote. And I know, like the one before it, I know that the oblique asymptote is going to be in the form of a line. I'll explain, or we'll address that shortly. So let's go in here and let's clear out y1. I'll put my negative. I don't know, I like to put parentheses around this anyway. So 4x raised to the third. Get out of the power, close the numerator, divide by, open denominator, 2x squared minus 1, close the denominator. Okay, so I'm going to push graph, and here comes, there comes the line. I have a little issue though. This graph, this graph is crazy looking. This graph looks something like this. And it does this. That's hard. Okay, so that's what the graph kind of looks like. But my asymptote is a line that's rising. Notice that as we move away from the origin in both directions for x, the graph is not hugging that line. But what if that line has a negative slope? And I press graph. Now let's see what happens. It's going to be, oh wait, hang on. I know something a little different here. It actually shouldn't be negative x, it should be negative 2x. Now let's see if it looks better. So, that's much, much better. So notice the graph. As you move away from the origin, your blue graph hugs the oblique asymptote the further it goes away from the origin. So this particular function here is going to behave like the end behavior of this linear function. All right? So, one last one before we sum all this up. So now I have a y equals, I want to graph x to the fourth, x raised to the fourth, get out of the fourth, divide by, open the denominator, x squared minus 1, close it. And I need to get rid of that in y2. And I will graph. So here we have a graph. This one looks pretty cool. That looks something like this. All right, and then does something like this. Okay, so here is, here's what I think the oblique asymptote is. Notice it's not a line. As you look at this graph and you move away from the origin, your graph does not approach a horizontal asymptote or a linear function or a linear asymptote as you move away from the origin in the positive and negative x direction. So, what if I go in and I put this in? X squared. Let's see what it looks like. Well, how about that? If you look at the graph, the original graph, as you move away from the origin in the negative x and the positive x direction, notice that the blue branches here coincide with the oblique asymptote. So these three examples, the degree of the numerators were larger than the degrees of the denominator. Notice that the degree of the numerator, the difference between those degrees was 1. Same thing here, the difference between the degrees is 1. And here the difference between the degrees was 2. These two had linear oblique asymptotes. This one had a quadratic. So hopefully you figured out that if the difference between the two degrees is 1, then you will have a linear oblique asymptote. Same thing here. And notice that this linear oblique asymptote was negative, and it was because of this right here, the negative out front, so it makes the slope negative. And then this one, since the difference between the degrees is 2, that means that the oblique asymptote looks something like this, a quadratic. Oh, that is just really sad. But your quadratic, the quadratic, x squared, is going to be your oblique asymptote. Okay, so that was, hopefully, I'm really hoping that all of that was, for the most part, a review of stuff that you had in Algebra 2. And I'm hoping that it kind of refreshes your memory. I'm going to end this video, and then we will conclude the rest of the lesson in the third part video.